Hello, everyone. Today, we are going to discuss Semester 3 Mechanical Engineering and TIS Engineering Mechanics.
Thank you, Professor Nikita. This subject is the backbone of mechanical engineering and helps students connect theory with real-world engineering.
Hello and welcome. Every time you take a step or every time a car hits the brakes, there's this invisible force at play. It's one of the most important and honestly often misunderstood forces in all of engineering. So today, we're going to master this force, the force of friction.
Think about it. One stops a massive speeding vehicle, and the other starts a fire from almost nothing. They seem like they're from totally different worlds, right? But the secret ingredient in both is exactly the same: friction. And understanding how to control this force, how to make it stronger, weaker, and how to use it, well, that's the key to so much of what we do as engineers.
So here's our game plan. We'll kick things off with the two main types of friction. Then we'll learn the rules that it plays by. After that, we'll see it in action in some pretty clever machines. And finally, we'll connect the dots and see why this is such a critical concept for your entire career. Ready? Let's get started.
Okay, first things first. Friction isn't just one single thing. It actually behaves differently depending on whether an object is moving or just standing still. This gives it two distinct faces: static and dynamic. So what's the real difference? It's simple, really. Just imagine you're trying to push a heavy cupboard. That initial really hard push you need just to get it to budge, that's you fighting against static friction. It's strong. But the moment it starts sliding, it suddenly feels a little easier to push, right? That's because you're now working against dynamic or kinetic friction, which is usually a bit weaker.
And that one single moment, just before the cupboard starts to slide, that is the breaking point. This maximum possible static friction has a special name: limiting friction. Think of it as the final barrier you have to break through to get things moving. That's right, it's limiting friction. Never forget that term. Now that we know the types, let's figure out what rules friction actually follows.
Right, so friction isn't just random. It follows a very clear set of rules or laws which are absolutely essential for any kind of calculation. Let's break down the most important ones.
Now, these are super important. That third point is especially interesting, isn't it? It means a really wide tire and a narrow tire, if they're made of the same material and have the same weight on them, will have the same frictional force. It's all about the roughness of the surfaces and, most importantly, the normal reaction force, which is basically how hard the two surfaces are being pressed together.
This brings us to the most important concept for all our calculations: the coefficient of friction, written with the Greek letter mu, or mu. You can think of it as a simple score that tells you how grippy or slippery a surface is. A high mu, like between a rubber tire and a concrete road, means high friction. A low mu, like steel on ice, means very low friction.
Here it is, the formula that ties everything together. The frictional force F is simply mu multiplied by the normal reaction R. Now, to make this super easy to remember for your exams, just think friction is a must for resistance. F equals mu R. Simple not.
And the answer, of course, is the coefficient of friction and the normal reaction. Okay, so we've seen the theory. Now let's look at how engineers use friction to build some truly amazing things.
So far, we've mostly talked about friction as something that stops things from moving. But smart engineers can actually use friction to their advantage. Two classic examples of this are the wedge and the screw jack. Think of a simple doorstop or an axe splitting a log of wood. That's a wedge. It's really just two inclined planes stuck together. You apply a small force on the top, and the wedge magically turns it into a much, much larger force pushing sideways. And guess what? It's the friction between the wedge and the wood that stops it from just slipping right back out.
And what about lifting something really heavy, like a car, so you can change a tire? For that, we use a screw jack. It's an absolutely genius machine that converts a small rotational force, that's you turning the handle, into a really powerful straight-line force that can lift an entire car.
Now here's the cool part. A screw jack is really just a long ramp, an inclined plane that has been wrapped around a pole. As you turn the screw, you are basically pushing the load up a very long, very gentle ramp. And it's the friction on those screw threads that performs the magic, holding the entire weight of that car safely in place so it doesn't come crashing down. You got it? An inclined plane. Okay, let's wrap this all up and see why any of this really, really matters for your future.
So we've covered a lot of ground: static versus dynamic, the laws of friction, and cool machines like wedges and screw jacks. But listen, this isn't just theory for exams. This is a fundamental force you will deal with in practically everything you design. Let's do a quick final recap. First, static and dynamic, the two states of friction. Then, limiting friction,
That's the breaking point of static grip. Next, F equals mu r, your most essential tool for all friction calculations. And finally, wedges and screw jacks, perfect examples of friction put to brilliant use.
This is so important to understand. When you master friction, you're not just getting ready to pass an exam. You are learning the secret to designing better brakes for high-performance electric vehicles, creating robotic grippers that can handle delicate objects without crushing them, and even designing the wheels for a rover that has to grip the dusty surface of Mars. Friction is both a problem you have to solve and an incredible tool you get to use.
So, I'll leave you with this thought. You now have the fundamental knowledge to control this invisible yet incredibly powerful force. You understand the language of friction. The only question left is, what are you going to build with it?